How high could you jump if you were on Mars? It's a fun thought. If you weigh 150 pounds on Earth, you'd instantly feel like you weigh just 57. You wouldn't just jump, you'd soar. A single leap could land you on the roof of a 3-story building. You could dunk a basketball on a 20-foot hoop. You'd feel like a superhero. But this superpower comes with an unimaginable price. We think of gravity as a limitation, a force that holds us down. But what if it's the only thing holding us together? What if, right now, Earth's gravity was suddenly reduced by 62%, matching the weak pull of Mars? This isn't a fun hypothetical. It's a cascading catastrophe, a chain reaction that would systematically destroy our planet, starting with the very ground beneath our feet and ending with the air we breathe. The change wouldn't just alter our lives, it would erase our world. The moment gravity weakens, the first thing you'd notice isn't the jump, it's the weight. Everything is wrong. Your brain, evolved over millions of years to expect 1 g of force, would be thrown into chaos. You'd feel a profound sense of vertigo and nausea. Every step would be an overcorrection, sending you stumbling and floating. Your internal organs, no longer held securely in place, would drift upwards in your chest cavity, putting strange pressure on your diaphragm. Even your own blood pressure, finely tuned to pump blood up to your brain against Earth's pull, would spike, creating an instant blinding headache. But our bodies are adaptable. The real problems start when we look at the planet itself. Gravity is the sculptor of our world. It's the ultimate limitation. It's the force that says to a mountain, you will grow this high and no higher. On Earth, our tallest peak, Mount Everest, is 8.8 kilometers high. It's a geological balancing act. The upward thrust of tectonic plates is in a constant battle with gravity, which tries to pull the massive pile of rock back down. On a Mars gravity Earth, that battle is hopelessly one-sided. With 62% less gravity, the tectonic uplift that builds mountains would be far less constrained. Our existing mountain ranges would rebound, stretching upwards. Over geologic time, new mountains could theoretically grow 2.5 times higher. Imagine an Earth where Everest rivals Olympus Mons, the 22-kilometer-high shield volcano on Mars. A mountain so tall, its peak pokes out of the breathable atmosphere. And those mountains would be angrier. When a volcano erupts on Earth, gravity is a crucial safety mechanism. It pulls the heavier chunks of ash and rock back down, limiting the eruption's blast radius. In our new low-gravity world, an eruption would be catastrophic. Magma and ash would be blasted significantly higher and wider. A single eruption, like Mount St. Helens, could now blanket entire continents in a thick, choking layer of dust, blotting out the sun for months. Even the oceans would be unrecognizable. Water, now feeling 62% lighter, would move differently. Rivers with less force pulling them downhill would slow their pace, carving wider, shallower, more meandering paths across the continents. But the ocean waves, that's where the true horror begins. When wind creates a wave, gravity is what pulls the water back down, creating a familiar crest and trough. With less gravity, that pull is weak. Waves would become massive, slow-moving, and unbelievably powerful. A simple storm surge could become a continental-scale tsunami, a wall of water hundreds of feet high, moving with terrifying, lazy power, not crashing onto the coastlines, but simply rising, washing over entire cities as if they were sandcastles. The world would be a twisted, taller, and more violent version of itself. But all of this would be irrelevant, because the real planet killer is already in motion, and it's happening above our heads. A planet's ability to hold an atmosphere is a simple, brutal calculation. Gravity. Gravity is what gives a planet its escape velocity. That's the minimum speed a gas molecule needs to achieve to break free from the planet's pull and fly off into space. Earth's high gravity gives it a powerful escape velocity of 11.2 kilometers per second. It's a gravitational cage trapping our thick, rich atmosphere. It holds on to heavy molecules like nitrogen and oxygen with ease. Mars, being smaller, has a weak escape velocity of only 5.0 kilometers per second. It was never enough. Over billions of years, the relentless pressure of the solar wind, a stream of charged particles from the sun, blasted Mars's atmosphere away, stripping it particle by particle. If Earth's gravity dropped to Mars's level, our escape velocity would plummet. The Great Escape would begin immediately. The lightest gases, like hydrogen and helium, would vanish first. They are already light enough to escape Earth, but are constantly replenished. Now they would be lost almost instantly. But the real crisis is with the air we breathe. In the upper atmosphere, molecules of oxygen and nitrogen, superheated by the sun, are already moving at incredible speeds. In our age 1G world, they are still well below escape velocity. But in our new 0.38G world, the calculation changes. Suddenly, millions of these high-energy molecules would find themselves moving fast enough to be caught by the solar wind and stripped away. Our atmosphere would begin to bleed into space. For those of us on the surface, this would trigger a terrifying, cascading failure. The pressure drops. As the atmosphere thins, the air pressure at sea level begins a relentless, one-way decline. Within a few thousand years, a mere eye blink in geologic time, our breathable air would be gone. But we wouldn't last that long. The second effect would kill us first. As the air pressure falls, the boiling point of water begins to drop. You see, the only reason water is liquid on Earth is because the weight of the 100-kilometer-high column of air above us is physically pressing down on it, holding it in its liquid state. As that pressure vanishes, a critical threshold is crossed. It's called the Armstrong limit. It's the point where the air pressure is so low that water boils at 37 degrees Celsius, our own body temperature. The saliva on your tongue, the tears in your eyes, the liquid lining your lungs, it would all begin to flash boil. Your blood itself would try to turn to gas, a horrific condition called ebullition. And the oceans? The oceans would die. As the pressure dropped globally, all 326 million cubic miles of Earth's water would begin to violently boil away into a rapidly thinning sky. The entire planet would be enveloped in a scalding, planet-wide fog, which would then be rapidly stripped away by the solar wind. The great engine of life, the water cycle, would become a one-way conveyor belt of extinction, pumping our oceans into the vacuum of space. Third, radiation. The atmosphere wasn't just for breathing, it was our shield. As it thins, it loses its ability to block lethal UV and cosmic radiation. The sun, once the source of all life, would become a sterilizing death ray. Any life that somehow survived the pressure drop and the boiling oceans would be scoured from the surface by a relentless bombardment of radiation. So what would be left of our blue planet? Our infrastructure, our dams, bridges, and skyscrapers, all meticulously engineered for 1 g of force, would fail. Many would collapse from the new, strange load dynamics. But it wouldn't matter. There would be no one left to see them fall. Our world, once teeming with life, would become a cold, silent tomb. The final landscape would be unrecognizable. It would be a world of impossibly tall, jagged mountains, their peaks scraping a thin, pinkish-purple sky. It would be a world of vast, dry basins caked in salt, the final tombstones of oceans that boiled away to nothing. The surface, bombarded by radiation, would be a sterile, rust-colored desert. The wind would be the only sound, a thin, meaningless whisper carrying radioactive dust over the bones of a dead world. Mars is not just a planet, it is a warning. It is a chilling monument to what happens when a world is too small, its gravity too weak to hold on to the precious, volatile ingredients of life. We look up at the stars and dream of lighter worlds, of flying, of being free from gravity's pull. But we have it all wrong. Gravity is not our prison. It is our protector. It is the invisible architect of our world, the force that holds our oceans in their beds, that anchors our atmosphere to the surface, and that keeps our feet firmly planted on the ground. It is the silent, constant force that makes Earth, Earth.